Welcome back to the deep dive. Our mission, as always, is to take really complex source material and just pull out the essential knowledge for you, giving you a serious shortcut to being well-informed.
Right.
And today, we are cracking open a really fascinating argument. It's centered on a 2025 book by the South African mathematician Edzai Zvobwo, and it's called Mathematics of Disruption.
This is a deep dive with some real weight to it, I think, because we're going to challenge a fundamental assumption that a lot of people hold.
Which is?
When you talk about the future of AI, most people's minds go straight to faster processors, GPUs, TPUs, just sheer computing power.
More muscle.
Exactly. But Zvobwo argues that the true engine, the real driver of the next wave of disruption, is actually mathematical elegance. It's about first principles.
Okay, let's unpack this then.
Yeah.
The author's central thesis, which is really the anchor for our whole conversation today, it's incredibly provocative. Disruption won't come from faster chips, it will come from mathematics itself. So this deep dive is all about moving you past those surface-level reports of what AI can do and getting you into a foundational understanding of why it actually works, but framed in a completely new way.
And the context here is just so important. This book, it wasn't written for a Silicon Valley audience that's, looking for the next IPO.
Right.
It's written specifically for African entrepreneurs, for engineers, students, policy leaders. The whole goal is to position South Africa and really the wider continent, not just as consumers of AI, but as leaders in developing it.
I found this concept he uses, mathematical sovereignty. That's a profoundly interesting idea.
It is.
It forces you to shift from this idea of technological dependency, just importing hardware and algorithms, to foundational self-reliance. It's about being able to truly understand and build the underlying tools yourself.
Exactly. It makes the scarce resource knowledge, not just capital. The book's argument is basically if you master the math, you own the technology's future.
Okay, but how do you get that message across? An academic textbook on math isn't going to get a policymaker excited.
Right, and Zvobwo recognized that. For this message to really land, it couldn't be some dry academic treatise.
So it's designed for the curious mind, which I take to mean it has to appeal to a data scientist, but also a politician who's trying to write policy.
Precisely. It's remarkably compact. I think the first edition is only about 55 focused pages.
Wow.
But what's really clever is the method. It uses this strong storytelling approach. It completely avoids the dense structure of a normal textbook.
How does that work in practice?
It creates its own little world to make these abstract ideas concrete. So you, the reader, are guided by three fictional South African characters, Thandiwe, Sipho, and Professor Khumalo. They take you on a journey through what Zvobwo calls 9 mathematical landscapes. And these landscapes are real places, spanning institutions from WIPS all the way to UCT.
And I guess the power of that approach is how it embeds the theory into local, relatable realities. It's not just abstract math, it's math applied to life as you know it.
That's where it becomes brilliant, yes.
Yeah.
They deliberately weave in specific South African challenges, and they turn these local constraints into catalysts for mathematical innovation.
Give me an example.
Okay, so instead of just talking about server racks in the data center, they talk about load shedding and energy fragility, how having intermittent power forces you to demand absolute computational efficiency.
That makes perfect sense. If you have limited access to reliable power, to compute time, then clever optimization isn't just a nice to have.
It's a necessity. It's about survival.
Yeah.
And they do this with other things too. They incorporate South Africa's unique assets and challenges, like managing the insane amount of data from the Square Kilometre Array Telescope.
CSSKA, right.
Or leveraging the multilingualism of the society. And they even use these simple everyday metaphors like optimizing the batching process for making vet cook.
Hold on, vet cook batching? That's fantastic.
It is, isn't it?
You're taking a concept like supply chain optimization and making it immediately intuitive through a local food example. It just shows that this kind of mathematical genius isn't confined to, university whiteboards. It lives in informal markets and kitchens.
Absolutely. The argument is that this local context creates a specific kind of mathematical intuition that the global north, with its seemingly unlimited compute resources, often misses.
And that localized intuition is the resource the book is trying to cultivate.
That's the core idea.
Okay, that sets the stage perfectly for the meat of the work then. The book synthesizes the true computational engine of AI into what it calls 6 mathematical pillars. This is the difference, it argues, between just using AI and being able to genuinely innovate with it. So let's dive into those 6 concepts, because this is where the deep part of our dive really begins.
Right. Let's start with Pillar 1, numerical precision. Now, at first glance, this sounds really simple, maybe like just counting, but it actually addresses the inherent fragility of all computation.
Okay, so when a computer calculates something, it's not using infinite precision, right? It's using floating point arithmetic, which means every single calculation is an approximation.
It is, yes.
We usually just ignore this, but Zvobwo argues that these tiny rounding errors, sometimes just 0.00001, they don't just vanish, they compound.
Exactly. They accumulate, especially across the millions or even billions of calculations inside a deep neural network.
Yeah.
And the real-world consequence of that is that these accumulated silent errors can lead to what we now call AI hallucinations.
A catastrophic failure of accuracy.
Total failure. And that 0.00001, it matters.
Yeah.
The book points out that in high-stakes fields, say in a resource-constrained clinic where a diagnosis might rely on a low-power device, or in high-frequency trading where microseconds matter, that tiny error is the boundary between a life-saving diagnosis and a really dangerous failure.
So numerical precision is sort of the silent guardian of trust in this whole system.
A very good way to put it. Now moving to Pillar 2, optimization. This is, for all intents and purposes, the engine of machine learning. Training a massive language model is basically the world's largest optimization problem. The AI is trying to find the one single best set of billions of variables or parameters that minimizes its error.
It's like standing blindfolded in a huge, bumpy, multi-dimensional valley, and you're just trying to find the lowest point. You can't possibly check every single spot.
You can't. And that's where the mathematics comes in. The book highlights gradient descent as the foundational tool here.
Okay, break that down.
Think of it as feeling the slope beneath your feet to figure out the steepest path downward. You just take small steps in the direction of the steepest descent.
And then you get the more sophisticated versions, Atom, RMS prop. These aren't just faster brute force methods, are they? They're mathematically clever ways of adjusting the size of your steps based on how bumpy the terrain is or how much progress you've made.
Exactly. And that cycles us right back to the South African context. When compute and electricity are scarce, you absolutely cannot afford to waste steps. Clever optimization becomes an economic imperative. You have to use algorithms like Atom to get to the solution in the fewest possible cycles.
Okay, so Pillar 3 then takes us into the messy reality of the world. Probability or reasoning under uncertainty.
Yeah, most of the data AI has to deal with is incomplete, it's noisy, it's uncertain. And the mathematical framework here allows machines to actually model that messiness. The book really emphasizes tools like Bayesian reasoning and Markov chains.
So for the listener who might not be familiar with Bayesian thinking, it's a really powerful idea. You start with an initial belief, a prior, and every time you get a new piece of data, even if it's incomplete, you mathematically update that belief to a more refined probability.
Right, so the machine is constantly learning. It's constantly adjusting its confidence level.
Which is critical for predicting volatile events.
Like those load-shedding schedules we mentioned. They are inherently unpredictable. A machine using these models can update its forecast instantly when new data arrives, like an unexpected generator failure, which allows for much better real-time decision-making, even with limited historical data.
It turns uncertainty from an obstacle into a variable you can actually manage.
Precisely.
That brings us to Pillar 4, causal inference. Now, this is a big one. Today's AI is amazing at correlation finding patterns. If X happens, Y often follows.
But it can't tell us if X caused Y. And that ability to move beyond just correlation, that's the holy grail.
Because correlation is fine for recommendations. If you like this movie, you might like that one.
Sure. But causation is necessary for intervention. If you want to build policy or engineer a stable system, you have to know which levers to pull to get the effect you want.
The book mentions complex mathematical tools here, things like do calculus and structural causal models. What's the simple way to understand why we need something like a do calculus?
We need it because we need to model counterfactuals, the what-if scenarios.
Ah, okay.
The do calculus lets an AI simulate an intervention. It can mathematically distinguish between simply observing that people who carry umbrellas tend not to be wet and the actual causal statement. If I do carry an umbrella, I will be less wet.
I see. That shift from passive observation to active intervention is why the book argues that causal inference is the pathway to true AGI, an AI that can genuinely reason, not just parrot patterns.
And that leads us to Pillar 5, quantum theory. Now, this might sound like a huge leap from load shedding, but the math is critical. We're talking about algorithms like Grover search or Shor's factorization that promise Well, exponential speedups over classical computers.
Right, by using quantum phenomena like superposition and entanglement. For the listener, superposition means a quantum bit can be a 0 and a 1 at the same time.
Allowing it to explore multiple computational paths at once. And the African connection here isn't just theoretical, it's physical.
The SKA telescope.
The square-kilometer array, yes, it's being built across southern Africa, and it will generate data volumes that are so massive, petabytes per day, that they will be impossible for classical computers to process efficiently in the long run.
So the SKA isn't just about astronomy. It's a monumental data challenge that forces you to find the next evolution of computing.
It does. The continent, by necessity, is placed right at the intersection of massive data needs and the requirement for these exponential speedups. It's uniquely positioned to engage with the coming quantum AI revolution.
The need is immediate.
It's existential for that project. Which finally brings us to Pillar 6, which is maybe the most philosophical, but also deeply practical. Anti-fragility and stochastic resilience.
This is a concept a lot of people know from Nassim Taleb, but Zvobwo grounds it mathematically in stochastic processes and robust optimization. Most systems aim for resilience, right? Bouncing back after a shock.
But anti-fragility means building systems that actually get better when they're exposed to shocks and volatility.
So the system doesn't just survive, it learns to thrive on disruption.
Correct. And the math behind this involves designing algorithms that aren't just robust to noise, but that actively use that noise, that stochasticity, to refine their performance.
And again, connecting this back to the context is so powerful. African societies have historically shown immense anti-fragility, learning and innovating under continuous systemic stress. The book suggests we can mathematically encode this inherited societal resilience into our AI architecture.
By using things like robust optimization, you can stress test your AI against unpredictable failures, making sure the system's performance isn't just okay in perfect conditions, but actually thrives when conditions are at their worst.
That is an incredibly powerful synthesis. 6 deep mathematical principles, all tied directly to localized constraints, creating this unique framework for innovation. But the book doesn't stop there, does it?
No, it doesn't.
It transitions into this ethical and philosophical dimension, introducing what the author calls the 9th pillar, the Ubuntu AI framework.
This is the critical, non-technical counterweight to all the math. It advocates for building AI systems that are fundamentally ethical, inclusive, and community-focused, all rooted in the African philosophy of Ubuntu.
Ubuntu. I am because we are. It's about communal problem solving. But how do you actually integrate a philosophy like that into algorithm design?
Well, it shifts the focus. It moves from optimizing for individual gain or profit, which often drives Western AI development, to optimizing for societal well-being and consensus.
Okay.
It means you build models that prioritize equity and resource allocation, that ensure the benefits of the AI are actually shared by the community it serves. The framework insists that this ethical grounding has to be built in the mathematical foundation from the start, not just bolted on as an afterthought.
Which makes the book's core message all the more resonant. This mathematical intuition that's needed to lead the next technological age. It isn't reserved for elite, far-off institutions. It can be cultivated through stories and frameworks that are rooted in local philosophy and everyday realities.
From navigating load shedding to ensuring equitable vet cook distribution.
Exactly.
It just reinforces the reality that hardware will always become a commodity. It will eventually democratize. The truly scarce resource, the one that determines who drives the next chapter of history, is that deep mathematical intuition and the ability to apply it ethically.
So what does this all mean for you? The primary insight from Zvobwo's Mathematics of Disruption is that the real engine of AI isn't just raw power, it's mathematical elegance. And that local, contextualized knowledge like what you find in the unique challenges of South Africa provides the intuition you need to innovate where others are just iterating.
And for those of you who are interested in getting this specific material, the book is published by Acalytica, which is Edzai Zvobwo's own platform. It's available in various formats, all designed to be accessible across the continent.
And the conversation we just had about connecting this profound mathematics to localized culture and ethical philosophies, it really raises an important question that we want to leave for you to explore next. If embracing mathematical first principles and unique cultural frameworks like Ubuntu can drive the next genuinely disruptive wave of AI, what other non-Western philosophical or mathematical traditions, things that have been previously overlooked by the technological mainstream, might hold the keys to creating fundamentally new forms of artificial intelligence?
That's the kind of exploration that will define true global leadership in the future of this field.
A fantastic thought to wrap up this deep dive. Go master the math. We'll see you next time.